Okay, let me show you the contents which I'm going to cover in this video. First, I will introduce the topic where I will also show you that what is the symmetrical and asymmetrical three-phase voltage or current vectors. Then I will explain about what is a positive sequence, negative sequence, and the zero sequence vectors. And then we will go through the operator A that will be utilized in finding these symmetrical components. And then I will explain the method of finding this PS, I mean the positive sequence, negative sequence, and zero sequence components from unbalanced three-phase voltage or current vectors. And then we will go for one example analysis, and in the last I will explain one MATLAB code to get the symmetrical components from the unbalanced vector. So let's go ahead. It is easy to analyze three-phase systems having the balanced voltage and balanced currents because the balanced vectors analysis of the single-phase circuit actually leads to the three-phase solution. So, but the situation becomes more complex if the voltage and current vectors in the three-phase circuit become asymmetrical or unbalanced. In this case, it is also not possible to directly apply the KCL and KVL in the three-phase systems. So actually these unbalanced voltage and current vectors are developed due to the unbalanced loads or maybe because of some faults in the power system, such as a single line to ground or line to line faults, etc. Here is one example of the balanced, the symmetrical three-phase vector. Here you can see the balance means where all the three vectors have the equal magnitude. For example, here 100 in this case, and also they have the equal angle between them. So in this case, they all have 120-degree with each other, and this is the corresponding sinusoidal waves representing these balanced vectors. And here the phase sequences ABC means first A will appear, then B will appear, and then C will appear like this. So this will be like this. So phase sequence is first red, yellow, and then blue. And this is the example where you can see one unbalanced or asymmetrical three-phase voltage or current vector where magnitudes are not same. Here you can see that 80, 120, and 50, and also the angles between them is also not same. Okay, if you compare this with the previous example, and these are the sinusoidal waves corresponding to these vectors. And here the phase sequence is ABC, the first red, and then yellow, and then blue. So this is how the balanced and unbalanced voltage or current vectors look like. The D. Fortescue in 1918 actually the first suggested a method of the symmetrical components to deal such complex problems of the unbalanced three-phase systems. He said that any unbalanced three-phase voltage or current vector can be broken or divided into the three components which are actually balanced or symmetrical. So these three symmetrical components are called positive sequence component, negative sequence component, and then zero sequence component. So let's see what are these components. So here you can see one example of the unbalanced voltage vector VA, VB, and VC. You can see the magnitudes are different, and also the angle between them are not equal. And its phase sequences ABC, the first red, and then yellow, and then blue. So this can be broken into the three component vectors. So first one is the positive sequence vector, second is the negative sequence vector, and the third one is the zero sequence vector. So if you see this positive sequence, it's a balanced vector. Here the magnitudes are same, and also the angle between them are equal. And its sequence is ABC. ABC, it is the same as of the input unbalanced vector. That's why it is known as a positive sequence. The red, yellow, blue. Similarly, you will get red, yellow, and blue. But in this case, it is the negative sequence balance vector. It is also a balance vector. I mean, the magnitudes are same, having equal angles between them, but the phase sequence is reversed. I mean, here you get red, blue and yellow instead of red, yellow and blue. So its phase sequence is opposite to the input balance vector. That's why it is known as a negative sequence vector. And this third group is actually the zero sequence balance vector. Balance because all three have the equal magnitudes, that are that's why they are overlapping with each other. So here you can see that VA0, VB0 and VC0 all are equal, and they have the same angles also. So these all sinusoidal waves are in phase with each other. That's why it has no sequence. And here you can see them once again. Now this process is reversible. Reversible means you can break this unbalanced vector into the three balanced components, and also if you want to get your unbalanced vector back, you can also do this reverse operation. So what is this operation? So if you want to achieve this VA, I mean the A phase voltage, then you can achieve it by adding this VA1, VA2 and VA0. If you add these three vectors, it should be a vector sum, not scalar sum. So if you add them, you will get this VA vector again. Similarly, if you add all the yellow one, VB1, like this, VB1, VB2 and then VB0. So then you will get your phase voltage VB. Similarly, if you add all the blue ones, I mean the VC1, VC2 and the VC0, then you will get your C phase, I mean the blue phase. So this process is a vice versa. I mean you can break the imbalance vector into the set of these three balance vectors, or by adding them you can get your signal back, I mean the balance vector back. Okay, so in this graph you can see the vector addition of these components, I mean this VA0, VA1 and VA2 to achieve the voltage of the phase A. Similarly, the voltage of phase B is achieved by adding these components, and then VC is achieved by adding these components. So we can see the vector sum here. So you can see that this is VA0, and then this is VA1 and then VA2, and after the vector sum we are getting this phase voltage VA. Similarly, we have the VB0, it's the same, then VB1 and then VB2, and after the vector sum we get this phase voltage yellow one, then VC0, VC1 and then VC2, and then we get this phase voltage VC. So in this diagram you can see the complete vector sum of all these vector components. Okay, and now let's see what is this operator A. So this operator A will be used in the method of finding these symmetrical components. So it is defined as the e power j 120. So obviously it is cos 120 plus j sin 120, and that is equivalent to minus 0.5 plus j 0.866. And in the polar form, it is simply 1 angle 120. So a square is in rectangular form, it is this, and in the polar form, it is 1 angle 240. So I mean the angle is doubled. And in the AQ, it comes again to the 360 degree, I mean the 0 degree at the same position. So what does this operator do actually? So if it is multiplied with some vector, then that vector will rotate by the 120 degree anti-clockwise. So for example, if you have one vector, let's say m angle theta, then this is your operator A. So if you multiply this, you can see that because of this one, your magnitude does not change, but the angle is changed, and now angle is theta plus 120. So your vector is rotated anti-clockwise by 120 degrees. So here you can see this in this example. So suppose I have one vector v angle 0, and if I multiply this vector with the operator A, the resultant vector will be this. So that is the AV. So obviously the magnitude will not change because the magnitude of the A is 1, but the angle becomes 120 instead of 0. So your vector is rotated by 120 degree, and if I multiply this vector again by A, then it will be rotated by 120 degree again in the anti-clockwise. So you can say that AV is multiplied with A again, A square V, or you can say that this vector is multiplied 2 times by A. So you get A square V, I mean the V angle 240. So with every multiplication of the A, your vector will rotate 120 anti-clockwise. So now you can see that A cube means once again there will be the multiplication and this vector will come again to its original position. So that's why it is 1 angle 0, right? So we will use this operator A in the method of finding the symmetrical components. So here you can see once again all these symmetrical components. I'm in the positive sequence, negative sequence, and then 0 sequence. So here the phase A, I mean the VA is achieved by adding VA1, VA2, and then VA0. Okay. And similarly, the phase voltage VB is achieved by adding VB1, VB2, and VB0. But here I will do something different, that I would like to represent all these components in terms of these components VA0, VA1, and VA2. So how it is possible? Let's see. So you can see that VB0 equal to VA0. So that is also written here. All these 0 sequence vectors are same in the magnitude. And now what about VB1? So let's see what is this VB1. So this is the VB1. If I want to write this VB1 in terms of the VA1, you can easily see that since it is a balanced vector, that means the magnitude of all these three are same. So how I can achieve this yellow from the red one? So obviously this is 120 and this is 120. So overall angle is at 240. So it is very clear, if I multiply A square with the VA1, then this red vector will rotate and will reach to this yellow position VB1. So I can write VB1 equal to A square VA1. So that's why you can see that the VB1 can be written as the A square VA1. Now what about VB2? This one, VB2. So how you can write this in terms of this red VA2? So obviously this is 120 degree. So if you simply multiply VA2 with only A, you will achieve VB2. So VB2 equal to A times VA2. So that's why the VB2 is written as A VA2. Okay. And similar operation we can do for this C vector. So here you can see that VC0 equal to VA0, that is already written, and the VC1 is A VA1. So let's see, where is the VC1? Okay, so this is the VC1. So I can write this VC1 in terms of the red. So this angle is only the 120. So VC1 means simply A times VA1. So here you can see that it is A times VA1. And now VC2, this vector. So this is VC2. Now represent this blue in terms of the red. So this is a total 240 degree rotation. So you have to multiply VA2 with the A square. So VC2 equal to A square VA2. So here you can see that VC2 equal to A square VA2. So now you can see that all B and C components are also written in terms of the A components. So that makes our analysis simpler. So let me assume that this is equation 1, this is the equation 2, and this is the equation 3. So I have rewritten all these equations here. So I can write these three equations in terms of the matrix equations. So you can see that VA, VB, and VC can be written in terms of the VA0, VA1, and VA2 because these are common in all three equations. So VA, VB, VC equal to 1, 1, 1, 1 A square A, 1 A square, VA0, VA1, VA2. Okay. or you can write like this. I mean, this matrix is represented by this matrix A, which is known as transformation matrix. So from equation 4 you can get this matrix. So obviously the A will go this side, so you will get this inverse. So VA0, VA1, VA2, so these are your symmetrical components. Okay, in terms of the unbalanced input vector, so the equation 5 is actually the answer which is showing that how I can achieve these symmetrical components, I mean VA0, VA1 and VA2 just by multiplying with this inverse A to this unbalanced input vector. So I will get answer from the equation 5. And now here in the equation 6, this matrix actually shows that how we achieve this A inverse. So the A inverse is obtained by this matrix, that is 1 upon 3. Here if you compare this with the A, you get we are getting the 1 upon 3, and also this for second and third columns are interchange. Okay, that's it. So from the equation 6 I can find all the symmetrical components from the input VB, VC and VA. So from equation 6, obviously I will get these three components from the input vector VA, VB, VC. So once I find all these three, VA0, VA1 and VA2, then you can see that from this set of symmetrical components, I have found only the three components. I mean the VA1, VA2 and the VA0. Only these red components I have found. So what about these blue, yellow components in each group? So this you can find from this table. So the all positive sequence members, I mean the VA1, this one, the VB1, this one, and the VC1, this one, you can find like this. So that is again with the help of the A operator. So let's say VA1 is VA1, it is already found. Then VB1, how you can find from VA1? Obviously it is 240-degree angle. So multiplying VA1 with the A square, you will get the VB1. And then VC1, you will simply multiply VA1 with the A. So you will get VC1. So similar operation you will do here. And here there is no phase sequence. All vectors are equal and in the same direction. So obviously the VA0 equal to VA0, VB0 is also VA0 and VC0 is also VA0. So from this table you can find these total 9 components, I mean 3 sets of 3 vectors. So now let's go through one example analysis where I can apply this theory. So for this, assume that the line currents in a 3-phase unbalanced star connected load are given by this. So this is the IR, I mean the R phase current, IY and IB. So here you can see that all the currents are not equal in the magnitude as well as the phases. I mean the angles between them are also not equal. So the phase sequence here is RYB. So since it is a unbalanced current vector, so you have to find the positive sequence, negative sequence and the zero sequence symmetrical components. So let's see how we can do this. So let's see the solution. So first we will write that matrix equations. I mean I will find these three components IR0, IR1 and IR2. In my previous theoretical part, I have taken the I mean VA0, VA1 and VA2. So instead of A here I'm using R. You can assume that this is a VA, this is similar to VB and this is similar to VC, okay. But here since this is a current vector, so we have to use the I for R phase, Y phase and B phase. So here that matrix equation is used. So this is your input vector. Okay, so I have substitute all the values of the input vector. So this is IR, this is IY and this is IB. So I can find these IR0, IR1 and IR2 just by multiplying these two matrices. So I will do row wise operation. So first to get this IR0, I will multiply only the first row with this column matrix. Okay. So obviously from this you can see that IR0 is equal to 1 by 3, 1 1 1 multiplied with this column. So it is IR plus IY plus IB. Okay, so that means 12 plus J 24, that is IR, then 16 minus J2, that is IY, and then minus 4 minus J6, that is IB. So by solving this, you get this 1 upon 324 plus J6, and this is equivalent to the 8 plus J 5.33. So it is in Cartesian form and it is in the polar form. So this is the first component, I mean the zero sequence component, that is 9.61 angle 33.69. And now go to this second row. So from where you can find this IR1. So IR1 is obviously equal to from this matrix equation, that is 1 into IR plus A IY and then A square IB. So you have to just substitute all the values from here. So 1 upon 3. So this is your IR, this is IR, and this is the A, and this is IY. This is A square. The value of A and A square I have already shown you in my operator A slides, and this is IB. Okay. So by solving this I can get this answer. So my IR1 is 0.8453 plus J 15.1067. So it is in Cartesian form, and in the polar form it is 15.13 angle 86.80 ampere. And now the third component is remaining, so that is corresponding to this last row, third row. So here you can see that IR2 is simply 1 upon 3 IR plus A square IY and AIB. So simply substituting all the values. So this is IR, this is A square, and this is IY, this is A, and this is IB. So solving this I get IR2 equal to 3.155 plus J 3.56, and in the polar form it is 4.76 ampere angle 45.45. So here you can see that I have found IR0, IR1 and IR2. So these are similar that we have found that VA0, VA1 and VA2. So what about the other components, remaining components? So this I have already shown in that previous table. So with the same example here we can also show. So this is your IR1. So this is the positive sequence group, I mean related to the number 1. So IR1 is already this, and IY1 is obtained by A square IR1. So that is this one, 15.13 angle minus 33.2, and IB1 is obtained by multiplying IR1 with the A. So here in this group you can see that all the magnitudes are same, 15.13, 15.13 and 15.13. That's why their magnitude is same, so they are the member of a balance vector. But let's see the angle also. So angle are 86.80 minus 33.2 and 206.8. So if we plot these three vectors, you will see that you get a balance vector group. Similarly, you get the negative sequence vector where you get IR2, IY2 and IB2. Again, you can see that all have the same magnitudes. If you draw this again, you will find you are getting a balance vector. And IR0 here you are getting the 9.61 angle 33.69. So as I said, all these waveforms are in phase. So there is no need of using this operator A, since all are aligned in the same direction. So IR0 equal to IY0 and equal to the IB0. So all three are same. So let me plot these vectors and see that how and what type of vector I achieve. So here you can see that IR1 is this one. So the magnitude is 15.13. So it means the length of this vector is 15.13, and the angle, you can see it is not exactly 90, it is slightly less than 90. So this angle is 86.80, I mean this angle. And for blue one, you can see that 15.13 angle 206. So its magnitude is also 15.16, and its angle is 206.8. And for yellow one, it is also 15.13, and its angle is minus 33.2. So this angle is minus 33.2. And similarly, you can see in this negative sequence vector. So IR2 is 4.76. So this is 4.76, and angle is 48.45. And then IY2, that is 4.76, and angle is 168. So this angle is 168, and magnitude is same, that is 4.76. And this blue one is at minus 71.55. So this is minus 71.55, and magnitude is 4.76. And for here, zero sequence group all are in the same directions and having the equal magnitude. So here you can see that how we can achieve these positive sequence vector, negative sequence vector, and the zero sequence vector from an unbalanced input voltage or current vector. So now let's see the MATLAB code to implement this method to find the symmetrical component. So first I'm taking the input from the user from the command prompt. I'm going to enter the three asymmetrical components. So user will enter all the three components in rectangular form, I mean in the form of A plus JB. So all three vectors will be entered here. So that will go into the ASC, and now I am separating those three values as a VA, VB, and VC. So VA, VB, VC are representing the unbalanced values. And now I am defining the operator A. You can see that minus 0.5 plus 0.866J. And then this is the matrix A, which is first row is 1, 1, 1, second row is 1A square A, and the third row is 1AA square. And then I'm getting the inverse of it. So that is equal to the 1 upon 3, this matrix, which it is already explained in the theory section. And this is how I'm getting the components. So here you can see that A inverse, I mean this A inverse multiplied with the VA, VB, and VC. So I'm getting SC, I mean the symmetrical component variable. So SC is carrying all the answer. So just separating the values from the SC like this. So all zero sequence components, I mean the VA0. So that is the SC1. So the first value of this is a zero sequence component. And as we have seen that VB0 is also equivalent to the VA0. VC0 is also equivalent to the VA0. So all zero sequence components are equal with each other. They are aligned in the same directions, having equal magnitude. And now separating all the positive sequence components. So the second value of this SC variable is actually the positive sequence value, I mean the VA1. And how to get the VB1? VB1 will obviously the A square VA1, right? So this is A square VA1, and then VC1 is simply A VA1. So this is how I'm getting all the VA1, VB1, and VC1. I mean the components of all positive sequence group. And here I'm getting all the components of the negative sequence group. And here in these two lines, I'm separating the real and imaginary parts of the input vector. So input vector is VA, VB, and VC. So I'm separating real and imaginary. So all real parts are going in VIR and all imaginary parts are going in VII. Actually, your input values are complex like this. Let's say VA equal to A plus JB, VB equal to C plus JD, and VC equal to E plus JF. So in VIR, I'm just getting all the real values, let's say A, C, and E. And in VII, I'm getting all the imaginary values like B, D, F. Okay, so this is actually done for display purpose and plotting. And on similar patterns, I am separating all the real and imaginary parts of the zero sequence vector. And then I'm separating the real and imaginary parts of all positive sequence vectors, and then similarly doing for negative sequence vector. Actually, this I have to do for plotting purpose. And to display the values in the command prompt area, these are the codes. So I'm displaying their values in the Cartesian form. So here you can see that with help of this display function, I am displaying this value of VA0. So that is the zero sequence components. And this text will also be printed. That means VA0 equal to VB0 equal to VC0 and the value VA0. And here I am displaying all the positive sequence components. So here you can see that VA1, that is the text, equal to num2 string VA1. So VA1 is a value. So converting that into the string. So that's why you can join all these strings to make a single string txt. And then with the help of the display, you can display this. So similarly, you are displaying all the negative sequence components here. So you will see the outputs when I will run this program in the MATLAB. And here, this is actually the plotting. So first I am plotting the input vector with help of the subplot. So here I am using the compass MATLAB inbuilt function. So with help of this compass command, you can plot your vectors in form of the arrows, I mean in polar form. So their length is actually the magnitude, and their angle theta is angle from this horizontal axis. So I'm using the color code. I mean the first component with the red, and then second with the white, yellow, and then blue. And here I'm changing their width, I mean the line width or thickness. So this is the asymmetrical input vector. I mean this is the input plotting, and here I'm plotting all the zero sequence vectors again with the compass command. And here I am plotting all the positive sequence vector with the compass command, and here I am plotting the negative sequence vector with again that compass command. So this is a simple MATLAB program. Let me run this program in the MATLAB and show you that what output I will achieve. So this program I have already written. So I will simply execute it by pressing this run button. So, okay, so now it is asking me to enter the asymmetrical components. Enter the three asymmetrical components. So this is how I can enter the components inside in this array. So this is my first components 12 plus J24. The same value I am checking here, which I have already covered in the example analysis. So you can match the results. And the second one is a 16 minus 2J or 2I or minus 4 minus 6I. So this is how you can give these three values related to your unbalanced voltage vector or current vector. So I will simply press this enter and I will get the answer. Okay, so in this command prompt, let me simply minimize this. So in the command prompt, you are getting all the answers. So for example, here you can see that zero sequence components are VA0 equal to VB0 equal to VC0, and that is 8 plus 5.33J or I. So it is similar to what you achieved in that theoretical section. And here you can see the positive sequence components. I'm in the VA1, that is 0.845 plus 15.1 J, and VB1 similarly you can see the VC1. And here you can see the negative sequence components VA2, VB2 and VC2. So here you can see all the sequence components and their corresponding value, and this is actually showing me their graphical representation. So it is giving me the clear picture. So the first one is showing the asymmetrical input vector. So here you can see that this is the asymmetrical or unbalanced current vector having the unequal voltages and angles, and it is divided into the three groups. So this is the first one. So that is the zero sequence vector. So all three are aligned in the same directions. And this is a positive sequence vector. So all three are of equal magnitudes, some 15 point something, what we achieved in that theory section. And this is the negative sequence vector. Okay, so here you can also match the phase sequence. So if you match the phase sequence, positive sequence with the input vector, you will get the same phase sequence. I mean red, yellow and blue. So here red, yellow and blue. So that's why it is known as the positive sequence. And in the negative sequence, you will see that the phase sequence is just reversed. So you are getting red and then blue instead of yellow. So you are getting in the anti-clockwise direction, red, yellow, blue. And this is the clockwise direction, red, yellow, blue. So this is the reverse phase sequence. So that's why it is known as the negative sequence vector. So this is what we have achieved in this MATLAB program. So here in this tutorial, we have seen that how we can decompose or break an unbalanced voltage vector into the three components which are symmetrical vectors such as positive sequence, negative sequence and zero sequence. So I hope you have enjoyed this video. So thank you very much for watching this video. Please like it, share it. So wait for the next video. Till then, goodbye.